Hello and welcome to Multiparadigm Data Science with the Wolfram language. Section 4, Assembling a Multiparadigm Toolset. In this section, we are looking at various algorithms and techniques that allow us to analyze the data from the perspective of multiparadigm data science, maintaining a workflow driven by questions. We've looked at classification as a technique to answer questions of the type, is this A or B? Does the sample belong to class 1 or class 2? For example, is the image of a healthy or a cancerous tissue? Is the individual high credit risk or low? And so on. Now let's look at predictive modeling techniques that allow us to answer questions like how much or how many. For example, how much should the price of a home be? How many runs will a baseball player score in the season? What will be the yield of a power plant this month? And so on. Regression is the task that seeks to answer such questions, while classification attempts to predict a discrete class label for the sample. Regression aims to compute a continuous target value or number given the features of the sample. Just like classification, it is a supervised machine learning task that uses training examples to learn. Here's some training data where each sample has two features, age and income, and a pre-recorded credit score. This is the target value we'd like to predict for new samples. Using this data, we'd like to infer a function to map from the feature values to the numeric target. And once we have that function, we can use it to predict a target when given the feature values of a new data point. In linear regression, the model or function which predicts the target or response variable, that is the score in this case, uses a linear combination of the predictive variables or features, in this case age and income. Here is the predicted credit score for a new sample with age 35 and income 65,000. And this is a fitted model against the data points showing the credit score for an income of 50,000 across an age range of 20 to 60. While linear regression is a commonly used technique, it is far from being the only one. The Wolfram language has a machine learning superfunction, Predict, which facilitates the multi-paradigm project workflow by automating the process of learning a predictor function, selecting the optimal algorithm according to the available data. Using this data set with height, gender, and age, we can use Predict to create a function that will predict the age from height and gender. Predict is able to handle different types of data, including numerical, textual, sounds, and images. Here's another example where the input is the image of a gauge reading and the output is the actual numeric value of the reading. The predictor function can predict a value given a single new input or a list of inputs. And while it provides the predicted value by default, it can also be asked for a distribution of the predicted value conditioned on the input. We can get more detailed information about the predictor function to understand what is actually going on behind the automated machine learning. Let's look at another example of training a predictor to predict the mean value of properties in a neighborhood of Boston, given certain features of the neighborhood. It's not enough to just create the predictor function. We need to evaluate the performance of this function to see if it is really making sense, if it will predict reasonable values for real-world samples. So we test and measure its performance against some test data with actual known target values. A comparison plot shows the predicted values against the actual values, the dashed straight line representing the perfect predictions, and the standard deviation gives the root mean square of the residuals. Here is a complete report on the predictor's performance. While Predict provides the convenience of automated machine learning, it also allows the freedom to customize the training process by selecting the method as well as setting its hyperparameters. This dataset has the average daily wind speed at 12 meteorological stations in the Republic of Ireland from 1961 to 78. Let's use the data from January of each year from 61 to 77 for training and reserve the data from January of 1978 for testing. We'll try to learn a predictor to compute the value of the wind speed at Dublin as a function of the wind speeds at other places and also the date. The gradient boosted trees method produces a prediction model in the form of an ensemble of decision trees. The trees are trained sequentially with the goal of compensating for the weaknesses of the previous trees. We are using it for regression in this example. Here's a comparison of the predicted values for the test data with the actual values of wind speed. The residual plot and the residual histogram show the predictions are mostly trailing the actual values. These are the hyperparameters selected by the automated machine learning procedure. We can choose to retrain the classifier and tune the hyperparameters. For example, let's set the value of the boosting method to gradient one-side sampling and retrain the classifier. We can see how the predictions change for the new classifier on the test set. As mentioned earlier, Predict attempts to optimize the choice of an algorithm based on the input. It can choose from among linear regression, nearest neighbors, decision trees, gradient booster trees, neural networks, random forest, and Gaussian process. For this dataset, let's train a random forest and a Gaussian process predictor. Random forest is an ensemble learning method again that can be used for both classification and regression. It operates by constructing a multitude of decision trees. The forest prediction is obtained by taking the most common class or mean value tree predictions. Each decision tree is trained on a random subset of the training set and also uses a random subset of the features with a bootstrap aggregating algorithm. The Gaussian process method assumes the data was generated from a Gaussian process. In the training phase, the method tries to estimate the parameters of the covariance function. The Gaussian process is then conditioned on the training data and used to infer the value of a new example using Bayesian inference. As we can see here, the Gaussian process predictor is smoother and handles small datasets better than the random forest. And we can also see the difference in training times. Among other ways to customize the predict function to have more control over the training process, we can specify the utility function. The default utility function for predict is the Dirac delta utility function, which corresponds with the value for the highest probability density being predicted as the target. We can define a different utility function that penalizes the predicted value smaller than the actual value. And now we have a different predicted value for the same input. The performance of the predicted function can be optimized for training speed, actual runtime speed, memory usage, or accuracy of the predictions. And this can be done by setting the performance goal option. By default, it tries to balance between the prediction speed and performance. For a really simple interpretable model, the Wolfram language offers FindFormula to find a function or formula that approximates the data. Say you want a formula to calculate prime numbers. Here are the first 100 prime numbers. We can find a formula to fit the data and use it to compute estimates approximating the next 5 prime numbers. Here's a comparison of the fit with the data for the first 300 primes. So in summary, we looked at some predictive modeling techniques for regression tasks to predict target value for unseen samples based on values of previously seen samples. We looked at the machine learning superfunction Predict and some of the algorithms it can use internally. We also looked at evaluating the performance of the predictor function and retraining the function after setting model hyperparameters. Early on in the segment, we took a brief look at linear model fit as a quick way to build a linear model for regression, and we concluded with FindFormula, which builds a simple interpretable model for univariate or time series data.